Economists have a very precise way of defining what efficiency of or lack of waste mean, and I want to teach you what that notion looks like in this video. The notion, which by the way is called in economics Pareto optimality, is built around the notion of a Pareto improvement test. So let me describe first what this means. So definition: a feasible allocation alpha 1, we put that as a superscript, Pareto improves over a feasible allocation alpha 0 if the following two things are true. First, the utility of I at the new allocation is strictly greater than the utility of I at the allocation 0 for at least one person I, one I. And second, these utilities at the new allocation are greater or equal than at the other allocation for all I. Let's think a little bit about what this means. It means that if you start an allocation alpha 0, you can Pareto improve it with using alpha 1. Basically, if you can make at least one person better off, strictly better off, maybe more, without hurting anyone. So if you want to see this graphically, for example, imagine that you have a plot in which you plot the utilities of everybody at the first allocation, and here you plot the utilities of everybody at the new allocation, and here you have the 45-degree line. For alpha 1 to improve in alpha 0, it has to be that nobody is below in this quadrant. So an allocation, for example, that has a bunch of people there and only one, let's say here, strictly better off, that is a Pareto improvement. But if you have an allocation, for example, that has almost everybody better off, but one person worse off, that is not Pareto improving. Let me make several remarks about this notion. Remark number one, you should think of this as a test for a detector of inefficiency. And the idea is that we start with an allocation alpha 0. We want to check whether it is efficient, so we run this Pareto improvement test with other allocations to see if we can detect an inefficiency. Clearly, if the allocation alpha 1 Pareto improves alpha 0, that is a detection of an inefficiency. Second remark that is very important, notice that the notion of waste is defined around the utilities. It doesn't really matter how people are consuming, exactly what they're consuming. We care about their utilities because that's what they care about. And the third thing is, notice that the definition of a Pareto improvement test uses the notion of a feasible allocation. That is critical because I can always improve on any allocation by imagining non-feasible allocations in which more and more and more resources are present. So really, for saying that something is inefficient, it better be the case that you find a Pareto improvement with another feasible, i.e. realistic allocation. Now we're ready to define the notion of Pareto optimality. So definition, a feasible allocation alpha is Pareto optimal, and we will sometimes abbreviate this as PO, if there doesn't exist another allocation, feasible allocation, another feasible allocation alpha hat that Pareto improves over alpha. It's a little bit of a weird notion if you're not familiar, so let me describe it graphically with some intuition. So we have an allocation alpha. It's feasible. And we want to check, is it efficient? And what we have to do is look at the set, the back of all possible feasible allocations, or other feasible allocations. And for each one of them at a time, we're going to apply the Pareto improvement test. So we say, if we move from here to here, can we Pareto improve? No. If we move from here to here, can we Pareto improve? No. Now, if this is no for everything, then we can conclude that alpha is Pareto optimal. Why? Because there is no waste in the sense that it's not possible to move to another allocation that makes at least one person better off without hurting someone. On the other hand, if at some point when we are doing the checks, we find that the Pareto improvement test can be passed by moving from alpha to another, let's say alpha hat allocation, then we have to conclude that alpha is not Pareto optimal. Why? Because it didn't pass negatively in some sense the Pareto improvement test. There is possible to move to another allocation that makes at least one person better off without hurting anyone. That is clearly wasteful from a social point of view. In other words, is not efficient. I want to show you a couple of examples that illustrate the notion of Pareto optimality and some properties or some interesting aspects of it. Let me emphasize that these examples are not particularly realistic. They are really designed to make you think about the notion of Pareto optimality. So the first example, think of an economy with two consumers. So there are two consumers, and both of them have preferences U of Q, M is equal to M. They only care about how much of the good M consumes. They have endowments WI. They come to the economy with endowments WI of good M. And there is no production. It's just what we have been calling, in other examples, a pure exchange economy. Okay? So what is a feasible allocation here? What is a set of feasible allocations? I hope it's easy to see that we can plot it in a line. This line has a length equal to the total endowment of good M, and an allocation is going to be a point that basically tells me how much consumer 1 gets and how much consumer 2 gets. And any point in this line is a feasible allocation. I hope that's obvious to you. What may not be as obvious, and it's going to illustrate a beautiful point about Pareto optimality, is what is the set of Pareto optimal allocations. Well, in this very simple world, is going to be the same. Why? Any point in the set of feasible allocations have the property that if we move to another allocation, hurts one of the people. Let's say start here, move to the right. That makes person 2 worse off because they get less of good 2, and that's the only thing that they care about, and vice versa if we move to M1. So this is a case in which every possible feasible allocation is also a Pareto optimal allocation, and it should be very easy to see from this point a key feature of Pareto optimality, that it has nothing to do with equality. This person getting everything is Pareto optimal, this person getting everything is Pareto optimal. In fact, any possible distribution is Pareto optimal. Here is another extreme example designed to illustrate another aspect of the notion of Pareto optimality. So consider a very extreme and unrealistic case in which there is only one consumer and only one firm. So the number of consumers is equal to the number of firms is equal to 1. And let's start by plotting what is the set of feasible allocations. So I'm going to draw a diagram here that has the amount M consumed by the consumer and the amount Q consumed by the consumer. Now, clearly, the point at which he consumes no Q and W is feasible, but you can imagine also using the film technology to produce something and say, getting a curve of feasible consumption like this. Now, how do we think about this? Any point in this curve has coordinates like this, which are Q and the W minus the cost of producing Q. That is feasible because basically all of the endowment is used to producing Q, and then the rest is consumed by the consumer. That satisfies the feasibility constraint. So any point with those properties, and this line extends down, is a feasible allocation. Now we can think of this jump here as the semi-fixed cost that the firm needs to pay. This is an example, by the way, with no fixed costs. Otherwise, we will need to change the details a tiny bit. You can play with it if you want. Now, what is the set of feasible allocations? It is this point, or it is basically this line. All of these are feasible allocations that can be achieved in this market. Now the question is, what are the Pareto optimal allocations? And I'm going to plot those in red. So actually, just for reminder, let me call black equal feasible allocations. Now, the first thing I'm going to do is draw the preferences of the consumer, the utility function of the consumer in this space. Let's say something like this. These are the indifference scores, the levels combination of Q and M that gives the same level of utility to the consumer. Now, I claim that this point is not Pareto optimal. Well, it should be obvious to you that that point, let me call it alpha, is not Pareto optimal because any alpha hat in this set improves on alpha. So that cannot possibly be Pareto optimal. In fact, if you are following the logic, you should be able to see that the only Pareto optimal point here is going to be this point that I'm going to draw in red, at which the utility indifference scores just touch this feasible set. That is the Pareto optimal allocation here in this particular example. So in red, I'm plotting the Pareto optimal. Now, why is that the only one? Well, because it's the only point that doesn't have this feature that I can find another allocation that is feasible and makes the consumer better off. Now, 2 comments. In this particular example, we can still worry about Pareto optimality even if there is only one consumer. And the key trade-off here is Pareto optimality also tells you something about what is the optimal level of production. The second thing is, please do not infer from this example that in general the Pareto optimal allocation need be unique. In economics, in general, as illustrated in part by the previous example, there can be many Pareto optimal allocations. So don't think that that is, even though many of our models will have that property, don't think that that is a general property of economic models.